Okay, in this video we'll talk about the solution for assignment 5. So let's begin. So let's read the question 1 first. So the magnetic flux through the loop varies according to the relation like this. This is different from the one in the textbook. So phi b is in milliwebers and t is in second. No problem, the SI unit. What is the magnitude of the EMF induced in the loop for when t equals to 2.7 seconds? And B is what is the direction of the current through R? This one R to the left or to the right? So for this problem, the physics is something like we have a time varying magnetic field, which means the magnetic flux through this loop is also time varying. In this case, according to Faraday's law, as long as we have time varying magnetic flux for a loop, then it will generate an induced electromotive force in this loop. So there will be current going around. And thus, in this question, it asks you to calculate the magnitude of this EMF, magnitude of the EMF, and also the direction throughout. So let's begin. Okay, according to Faraday's law, the induced EMF is the derivative of the magnetic flux with respect to time. So it is something like this. Phi b is given by the question, so it is nothing but 2 plus exponential to minus t over 5 sine 6 pi t, something like this. So the first term is a constant, so the first derivative is 0. And then for the second term, there is two functions multiplied together. So we need to use the product rule. So we first take the derivative of the first term, exponential to minus t over 5. So we have exponential to minus t over 5, and then use the chain rule, minus 1 over 5. And then we also have another negative sign, so we have 1 minus 5. And then multiply by the second function, sine 6 pi t, something like this. Then for the second term, will be take the derivative of the second term, sine 6 pi t, which will be cosine 6 pi t. And then the chain rule, we multiply by 6 pi. And then we multiply by the other function, which is exponential to minus t over 5, something like this. And then we have another negative sign, so something like this. Okay, so we have the expression for the induced EMF. So E for t equals to 2.7 seconds. So we substitute t equals to 2.7 seconds into the expression. So we have 1 over 5 exponential to minus 2.7. 2.7 over 5. And then we have sine 6 pi times 2.7. And then for the second term, minus 6 pi exponential 2 minus 2.7 over 5. And then cosine 6 pi times 2.7. So one thing you need to care about is when you use the calculator to calculate this term and also this term, you should be care about whether you use the degree mode or the radian mode. Actually, this term is in radian. 6 pi times 2.7 is in radian. It's in radian because we don't have something like 2.7 degrees, something like that. Then it would be degree. But here it is not that case. So this is an expression in radian. And if you need to convert it into degree mode, usually the default setting for a calculator will be in degree mode. Then you will need to multiply this one by 1 over 80 degree over pi, because 1 over 80 degrees is actually pi. So you need to multiply this term to make it in degree. Otherwise, you calculate a different value. So let's move on. So when you press the calculator, the answer will be minus 0.0685 minus 8.886, so which will be minus 8.82 millivolt. So actually in the question it asks you about the magnitude, which means that the absolute value of E, t equals 2.5 second, will be 8.82 millivolts. So this is the magnitude of the induced EMF. And the next, for part B, so this is part A, this is part A. So for part B, we need to determine the direction of the current throughout. So for this question, as long as we have B is positive when B is pointing out of the page. This green dot means out of the page. So which means that when B is positive, it is out of the page. So when we apply the right hand rule, we use our thumb pointing out of the page, and our other 4 fingers are counterclockwise. So counterclockwise is the positive direction. When we apply the right hand rule, we can drawing something like this. So we have 5 fingers in a hand. So this is our thumb. When this one is pointing out of the page, so this is your thumb pointing out of the page, and then your 4 finger will be counterclockwise. So this is a positive direction when we define B is pointing out of the page. Okay, so this is a positive direction. However, in this question, we calculate that the induced EMF is negative at t equals to 2.7 seconds. Actually, it should be also at 2.7 seconds. So in this case, it's negative. So the current is actually clockwise. The induced current is clockwise. So in this case, the current through the R is to the left. So for part B, at t equals 2.7 seconds, the current throughout is to the left. Okay. So for the next one, is something like this. Okay, so let's read the question. So a rectangular loop of n closely packed turn. So n closely packed turns is positioned near a long straight wire. So this is long, actually infinitely long. In this text, so long means infinitely long. So near a long straight wire as shown. What is the mutual inductance M for the loop wire combination if n is equal to a equals to B and L, something like this, A, B, L, and N and I, something like this. We actually don't need to know the I, so because we only need to care about the mutual inductance. So in this chapter, we know that we have briefly two kinds of inductance. One is self-inductance, something like an inductor, because you have a current, something like this, and then when this current going through a loop, and then you will generate the magnetic flux going through the other turn, and then this will this is the mechanism for the self-inductance. This is the mechanism of self-inductance, because according to the Lenz's law, it will generate a voltage drop, something like that. And for this case, as long as we have a current going through the wire, and then for this wire, it will generate a magnetic field. And according to the right-hand rule, it will be something like this. And actually, there will be some magnetic field crossing this area. And in this case, according to the so it will generate a magnetic flux across this area. And according to the definition of the mutual inductance, which is equals to N times phi over I. So phi is the magnetic flux across this area, and then the I is this I. So this is the mutual inductance. The current here will generate a magnetic flux for a loop which is independent of this. Not really important, but the loop is actually independent of it. But this will generate the magnetic flux for this loop, for this area. Okay, so let's begin our calculation. And actually, we need to calculate phi. N and I, we don't read. N is given, and I is not. I will be cancelled actually. So our target is to calculate the phi, generated by this current. So phi will be B dot dA across this area, And according to the right-hand rule, the magnetic field across this area will be pointing out of the page and actually perpendicular to the page. So actually B and dA you can also define it to be out of the page. A is out of the page. So B dot dA is nothing but BDA. And A is nothing but, so B dA, A is L dr, or maybe you can use dx dy, something like that. But actually we can actually use dr in this direction, and we can take r equals to 0 here. R is equal to 0 at the wire, at the straight wire. So this is r equals to 0, and it will generate. So this is r, and dr will be something like this. This is actually dr. So actually we need to sum over when r equals to a plus b, because we take r equals to 0 here, so that we need to consider the area for this part. And actually L is constant, because this is a rectangular. And we need to consider from r equals to a to here. So this is a plus b, r equals to a plus b. So this is r equals to a, this is r equals to a plus b. So we have the lower and upper bound like this, And in chapter 29, we know that the magnetic field generated by the long straight wire is mu 0 I over 2 pi r. That's why we call the axis r. But actually you can call it x, no problem. And so it's something like this. So this is B. And so mu 0 I L a constant over 2 pi a constant, and we have a plus b, so we have dr over r. Okay, so we will have mu 0 I L over 2 pi, and this one 1 over r, so it will be log r, and then we have we substitute the upper bound and lower bound and subtract them, so we have a plus b over a, then finally we will have mu 0 I L 2 pi ln 1 plus b over a. So finally we would like to calculate the mutual inductance M, which is N phi over I. N phi over I. So I will be cancelled, and we will have N mu 0 L over 2 pi ln 1 plus b over a. So we substitute all the number 100, and then mu 0 is 4 pi times 10 to minus 7. So we have 2 pi, so only 2 times 10 to minus 7 is remain. And L is 30 centimeter, so it is 0.3 meter. Ln 1 plus B is 12. B is 12 centimeter. A is 1 centimeter. So we have 12 over 1. And then finally, we will get the mutual inductance is actually 1 point. No, not 1 point. 15.4 microhenry. Yeah, microhenry. Let me double check because my notes are not matching. Yeah, 15.4 microhenry. 15.4 microhenry. So this is the solution for the second problem. I think it's still pretty simple. Okay, so that's all for the solution for assignment 5. And if you have any more questions, please let me know and I will try to answer your question. So see you.